Hello and welcome to Algebra 2 Lesson 30. In this video, we're going to learn about solving linear systems in two variables using matrix methods. So in this lesson, I want to talk a little bit about another method used to solve linear systems. So far we've learned how to use graphing, substitution, and elimination. But we're going to push ourselves a little bit further and now talk about matrix methods. So as we move higher in math, things are going to become more complex. Matrix methods allow for us to solve very large linear systems using a computer very quickly. So we're not going to cover all of the details related to a matrix. But what we will do is give an introduction and show one method for finding a solution using a matrix. So let's start out with the very basics here. So a matrix is an ordered array of numbers, and it's just a way to store numerical information. So you'll see my brackets here, and in the brackets you have two rows, two rows. This would be a row going across. So you have two of those, and you have three columns. So the columns are going down. So a matrix is named according to the number of rows and columns it contains. It's rows first, followed by columns. So as an example, if I see this matrix here, you see that you have 1, 2, 3 rows. So 3 going across. So 3 is the first number. And you have 1, 2, 3, 4 columns. So 4 is the second number. So this is a 3 by 4 matrix. Similarly, with this guy right here, you have 1, 2, 3 rows. So it's a 3 rows there. And you have 1, 2 columns. So this is a 3 by 2 matrix. So another little kind of definition that you'll come across, you have a square matrix. And let me highlight that. A square matrix has the same number of rows as columns. So here I have 2 rows and 2 columns. So this is a 2 by 2 matrix. As another example of a square matrix, we have 3 rows here and we have 3 columns. So this is a 3 by 3. Right? And you can have anything by anything. So you can have 4 by 4 or 27 by 27, as complex as you want to make that. All right, so I want to start out today with a very basic example. So we have the linear system 2x minus 5y equals negative 14. We have 7x minus 7y equals 14. I have here start with an augmented matrix. Before we get into that, I want you to notice that we have each equation already written in standard form. So you want to start by putting ax plus by is equal to c. Both equations in this form. Now, once you've done that, you can write this augmented matrix. What this is I'm going to take the numerical information only. So in other words, the coefficient for x is a 2. So I'm going to write a 2. The coefficient for y here is a negative 5. So I'm going to write negative 5. The constant is negative 14. So I'm going to write negative 14 there. So that's my first row. It represents the numerical information from the first equation of the system. My second row is the same thing. So I have a 7 for x. I have a negative 7 for y. And I have a positive 14 as my constant. Now I'm going to put my brackets here. And with the augmented matrix, we use a vertical bar to separate the coefficients from the constants. So my coefficients are here. Okay, these are the coefficients. And these are my constants. So I'm just going to put a vertical bar right here. So from this information here, we can get a solution for x and y. Now, in order to do that, we're going to use these elementary row operations. And there's 3 of them. So let's go ahead and look at that. All right, so I have here, we can manipulate our matrix using row operations. These produce matrices that lead to linear systems with the same solution set as the original system. All right, so here's our row operations. The first thing is that we can interchange any 2 rows. That makes sense because if I had an equation and another equation, it doesn't matter which one I write on top, right? I can switch that around as much as I want. The second thing is we can multiply any row by a non-zero number. Well, that makes sense. I can multiply both sides of an equation by a non-zero number. I could divide both sides of an equation by a non-zero number, and the equation would contain the same solution set. So the last row operation we're going to talk about, row operation 3, is a little bit challenging to understand. So we have here that we can multiply a row by a real number and add this to the corresponding elements of any other row. So when people first see this, they say, well, what makes this legal? Well, essentially, we're using the same basic principles that we used when we used the elimination method. So we're going to quickly look at a different example, and I want to just cover why this would work. So let me just take an aside from that problem that we're currently working on. So just put that to the side, take out a fresh sheet of paper, and I want you to work through this very basic example with me. So if we have 2x plus 3y equals 11, and we have x plus 2y equals 7. So we can easily solve this using elimination at this point. So I want to do elimination, and I want to do the matrix method. I'm not going to go all the way through it. I'm just going to go to the part where it's obvious what the solution is. So if I wanted to solve this with elimination, what would I do? Well, let's go ahead and say this is equation 1 and this is equation 2. Well, I know that I can eliminate x if this was negative 2 here. And the way I can do that is I can multiply both sides of this equation by negative 2. So if I did that, what I would have is a negative 2x plus negative 4y equals negative 14. So I could write that I have 2x plus 3y equals 11. And I have this other one, negative 2x minus 4y is equal to negative 14. Okay, so now we all know at this point that the x variable would be eliminated. So I could add the two left sides of the equation, set that equal to the sum of the right sides of the equation. So 2x minus 2x would be 0. X is eliminated. That's gone. 3y minus 4y is negative y. And this is equal to, let me kind of move this down a little bit, 11 minus 14, which would be negative 3. So we all know that y is 3. So y is 3. Now I can plug a 3 back in here and figure out what x is. 2 times 3 is 6. So I would have x plus 6 equals 7. We know x would be 1, right? X is equal to 1. Now, I want to just show you this real quick using a matrix so I can relate the steps. So the first thing is we want an augmented matrix. So I just told you we take the numerical information. Again, these equations are written in standard form. ax plus by equals c. So I have my coefficient for x, my coefficient for y, and my constant written in that order. I'm going to write it in the same order here. So this is understood to be a 1, so just a 1, a 2, and a 7. I've got a vertical bar that separates the coefficients from the constants. Now, using the numerical information only, I can do the same thing that I did here. I want to think about how could I get a 0 here so that the coefficient for x is a 0, and x is essentially eliminated. I would have some number times y equals some value, which is what I had here. So I'm going to show you that. I can use the elementary row operations. I can say if I multiplied row 2 here by negative 2, which is exactly what I did here. Remember, I had the second equation, I multiplied it by negative 2, and I produced negative 2x minus 4y equals negative 14. So if I multiplied row 2 by negative 2, 1 times negative 2 is negative 2. 2 times negative 2 is negative 4. 7 times negative 2 is negative 14. And then I added those elements to row 1. So negative 2 plus 2 would be what? That would be 0. So I'd have a 0 here. Then negative 4 plus 3 would be negative 1. Then negative 14 plus 11 would be negative 3. Now I don't need to change this row here because I already have what I need there. So I can just leave this as 1, 2, and 7. okay? But it wouldn't matter if I wrote -2, -4, and -14 there. But for the purposes of working with a matrix, we're not going to do that. We're just going to leave this row unchanged. Now, I have the same information here that I have here. I know that the coefficient of x is 0, so x is eliminated. I know that the coefficient for y is -1, so basically I have -1y is equal to -3. So from this information here, I can solve for y, okay, and then I can go back and figure out what x is. Now, this isn't exactly how we're going to solve using a matrix, but it's just an example of how we can manipulate the numerical information to get a solution. So I want to return now to the official procedure. Again, this is just a little side note. You can kind of get rid of this now. And let's go back to the original problem. What our goal is actually going to be, we have this term known as row echelon form, and you're also going to hear reduced row echelon form. I'm going to cover both of them, but I want to focus on row echelon form for now. So what you want is ones down the diagonal. So starting at the top left, you have a 1. Then going this way, you'd have another 1. Now, beneath the ones, you're going to put a 0. Okay, so this has to be a 0. Now, you're going to have real numbers above and to the side. So this is A, B, and C just representing real numbers. If I have something in row echelon form, and again, these equations are AX plus BY equals C, well, I know that I'd have 1x plus AY is equal to B in this case, right? Just using generic information. And I know here that I have 0x, so x is eliminated, plus 1y, or just y, equals C. So from this, if I know y equals C, I can plug in for y here, and I can find out what x is. Again, we're just taking the numerical information and finding our solution. So again, this is row echelon form. So I want you to write that down. And then once we get this down, I'm going to show you reduced row echelon form, which isn't any more complicated. All right, so I want to return now to the system that we were starting with. So again, it's 2x minus 5y equals -14. It's 7x minus 7y equals 14. So let's copy this information, and we'll copy this and we'll bring it down to a new sheet of paper. So again, we have 2x minus 5y equals -14. We'll call this equation 1. And then for equation 2, we'll have 7x minus 7y equals 14. All right, so again, write the augmented matrix, just the numerical information. That's all we want. So we want 2, we want -5, and we want -14. We want 7, we want -7, and we want 14. A vertical bar will go right here to separate the coefficients from the constants. And our goal is what? Again, I want ones down the diagonal. So I want this to be a 1, and I want this to be a 1. So down the diagonal, okay, that's going to be a 1. Beneath the diagonal, I want a 0. And then these numbers here would be real numbers. So how do we achieve that goal? Well, again, we're going to use our row operations. So how could I make 2 a 1 using the row operations? Well, I could simply multiply every number in this row by 1/2. 2 times 1/2 equals 1. So if I do that, what would I get? 2 times 1/2 again is 1. -5 times 1/2 is -5 halves. And -14 times 1/2 is going to be -7. Now for this one, I have 7, -7, and 14. I haven't done anything there. Okay, so now that we have this as a 1, we want to make 7 into a 0. It's best to work a column at a time. So starting here and working down. If I wanted 7 to be a 0, what could I do? Well, I could multiply 7 by 0, but that's not going to work, right? We can't multiply both sides of an equation by 0 and maintain the same solution. That's a violation. So what I have to do is I have to multiply this row here by something and add it to this to get this to be 0. So first and foremost, what can I add to 7 to make it 0? Well, obviously negative 7. So that means I need to multiply 1 by some value, and it needs to give me negative 7, so that when I add it to 7, I get a value of 0. So 1 times what would give me negative 7? 1 times negative 7. So that means I'm going to multiply row 1 by negative 7. And when I do that, what am I going to get? Well, 1 times negative 7 is negative 7. Negative 5 halves times negative 7 would be 35 halves. And then negative 7 times negative 7 is going to be 49. So I'm going to take that information and I'm going to add it to each element here. So this row 1, I'm just going to keep it the same. Remember, I don't have to change it. Negative 7 plus 7 is 0. So 35 halves plus negative 7. So plus negative 7. I multiply this by 2 over 2. That would be negative 14 over 2. And 35 minus 14 would give me 21. So this is 21 halves. And then lastly, I have 49 plus 14. So 49 plus 14 would give me 63. Okay, so now let's scroll down. The next thing I want to do, since I have a 1 here and a 0 here, remember I want 1s down the diagonal. So how can I make this into a 1? Well, that's easy. 21 halves times the reciprocal, which would be 2 over 21, would equal 1. So just multiply row 2 by 2 over 21. So multiplying 0 by anything is 0. So let's just start out by saying this is 1, this is negative 5 halves, this is negative 7. So that's all the same. 0 again times 2 over 21 is still 0. 2 over 21 times 21 over 2 is 1. And then 63 times 2 over 21. Well, 63 divided by 21 is 3. So this cancels with this and gives me 3. 3 times 2 is 6. Now, what do I have here? Well, I have row echelon form. I have 1s down the diagonal. I have a 0 below. And I have real numbers here, here, and here. So once I'm in that format, I have enough information to get a solution. Remember, this is ax plus by equals c. So forget about this top row. The bottom row is basically 1y is equal to 6. So I know that y here is equal to 6. Now I can take this information and plug it in here. For this guy right here, I have that 1x, or just x, plus negative 5 halves times y is 6, is equal to negative 7. So I know if I do a little bit of math here, 6 divided by 2 is 3. Negative 5 times 3 is negative 15. So we would have x minus 15 is equal to negative 7. We would add 15 to each side of the equation, and we would have that x is equal to 8. So x equals 8, y equals 6. So I'm going to write that x equals 8, y equals 6, or the ordered pair 8, 6. Now, let's check this real quick. I'm not going to check any in the future because of the interest of time, but I just want to show you that this works. So we have 2 times, put in 8 for x, minus 5 times, plug in a 6 for y. This equals negative 14. 2 times 8 is 16, minus 5 times 6 is 30. This should equal negative 14, and it does. 16 minus 30 is negative 14, so negative 14 equals negative 14, so it works out here. For the next equation of the system, we have what? We have that 7x, so 7 times 8, minus 7y, y is 6, equals 14. 7 times 8 is 56, minus 7 times 6 is 42. Does that equal 14? Yes, it does. You get 14 equals 14, so it works out here as well. So I know you might be a little confused on this. It's okay. It's something new. It's something that you just have to practice. But hopefully you can see the concept and understand what we're doing. We're basically just taking the numerical information and we're using the elimination method, but we're doing it in a more compact way. So let's take a look at the next example. So we have negative 9x minus 9y equals negative 27. We have negative 5x minus 4y equals negative 20. So again, I'm going to take the numerical information here. So a negative 9, another negative 9, and a negative 27. I have a -5, a -4, and a -20. And again, you want to make sure that these equations are written in standard form. ax plus by equals c. Both of them on top of each other. Verify that the x's are in the same place, the y's are in the same place, the coefficients are in the same place, so that your information is correct. So you have your vertical bar, okay, that separates the coefficients from the constants. And so we have our augmented matrix. All right, so remember, we want ones down the diagonal. Okay, so we want this to be a 1, and we want this to be a 1, and we want a 0 below, and then these can be real numbers. All right, so let's get started. How would I make -9 into a 1 using the row operations? Well, that's easy. I can always multiply -9 by the reciprocal, which is -1/9. If I multiply -9 by -1/9, I know that this would be 1. If I multiply -9 by -1/9, again, I'm going to get a 1. If I multiply -27 by -1/9, this cancels with this, and I get a 3 here. So -3 times -1 would be 3. And then now I have this row -5, -4, and -20. All right, so now I want this next guy here, -5. Remember, I work a column at a time, so I want this to be a 0. So what can I do? Well, again, I want to add something to -5 to give me 0. Well, I know -5 plus 5 would give me 0. So in order to do that, I would multiply the first row here by 5, right? Because 1 times 5 would give me 5. So if I multiply the first row, 1 times 5 would equal 5. 1 times 5 would again equal 5. And then 3 times 5 would be 15. So I'm going to take these results here and add them. So my first row, I'm just going to keep it the same. 1, 1, and 3. So 5 plus -5 is 0. 5 plus -4 is 1. And then 15 plus -20 is -5. Now, it just so happens that this is an easy example, and I've already got what I want, which is row echelon form. I've got ones down the diagonal, I've got a 0 over here, and I've got real numbers here. So again, once we have it in this format, we can use substitution to find our solution. So I know that from this bottom row here, I would have 1y, or just y, is equal to -5. In the top part here, I have that x plus y, right, because I have 1x plus 1y, is equal to 3. So just plug in a -5 here, and you'd find that x minus 5 equals 3. Add 5 to each side of the equation, and you're going to get that x is equal to 8. So the solution for this system would be that x is equal to 8, y is equal to -5, right? Or as an ordered pair, you could say 8, -5. And you can pause the video, go back to the system, and check it. And verify that it's the correct solution. I've already done that, so I know that 8, -5 is the solution. All right, let's take a look at one more example. And what I'm going to do in this example, I'm going to show you reduced row echelon form as well as row echelon form. Okay, and I'm going to explain the difference between the two. So we have 5x minus 6y equals 24. We have 2x plus 7y equals -28. So again, ax plus by equals c. So you make sure your equations are in that format. Again, a lot of textbook examples are going to jumble things up. So it's not in that format. You've got to write it that way so your information is consistent. All right, so I have a 5, a -6, and a 24. The information here, I have a 2, I have a 7, and I have a -28. So I have my vertical bar that separates the two, right? The coefficients from the constants. And now we get to work. So again, we're going to talk about row echelon form first. So that's ones down the diagonal, a 0 over here, and real numbers here. So let's start with the first column here. How can I make 5 into a 1? Well, I can multiply row 1 by 1/5, right? 5 times its reciprocal of 1/5 gives us 1. So if I multiply 5 times a fifth, I get 1. If I multiply negative 6 by a fifth, I get negative 6 fifths. If I multiply 24 by a fifth, I get 24 fifths. And then row 2 stays the same for now. So 2, 7, and negative 28. Okay, so let's scroll down. Now, again, working at a column at a time, how could I make 2 into a 0? Well, I think about row 1 here. To get 2 into a 0, I've got to add 2 to its opposite, which is negative 2. So what can I multiply 1 by to get a result of negative 2? Well, of course, just negative 2. So if I multiply row 1 by negative 2, 1 times negative 2 gives me negative 2. Negative 6 fifths times negative 2. I know the negatives would cancel. You'd basically have 12 fifths. And then 24 fifths times negative 2 would be negative 48 fifths. So this is negative 48 fifths. So for row 1, I'm keeping that the same. So a 1, a negative 6 fifths, and then a 24 fifths. For row 2, I'm going to take the result that I got, and I'm going to add. So negative 2 plus 2 is 0. I'm going to have 12 fifths plus 7. So 12 fifths plus 7. I could write that as 35 fifths. 12 plus 35 is 47. And then the common denominator of 5 is what that's going to be over. So that's 47 fifths. And then if we think about the next result, you'd have negative 48 fifths plus negative 28. So negative 48 fifths plus negative 28 times 5 is negative 140. So I'd have negative 140 over 5. So if I add these two together, negative 48 plus negative 140, that will give me negative 188. So I'd have negative 188 over 5. All right, so the next thing I want to do is make this a 1. I want 1s down the diagonal, 0 below. I've already got this part. I just need this part. So let's scroll down here. And it's very easy. I just multiply row 2 by the reciprocal of 47 fifths, which is 5 47ths. So let's keep row 1 the same. So row 1 stays the same. A 1, a negative 6 fifths, and a 24 fifths. For row 2, again, if I multiply 5 over 47 by 0, I get 0. 5 over 47 times 47 over 5 is 1. And then 5 over 47 times negative 188 over 5. Well, I know the 5s would cancel. And negative 188 divided by 47 is actually negative 4. So at this point, I have enough information to get a solution. I know that y is equal to negative 4, right? So if y equals negative 4, I can plug in for y in this part. So I would have x minus 6 fifths y is equal to 24 fifths. Scroll down a little bit. And again, y is negative 4. So what we're going to get is that x minus 6 fifths times negative 4 is equal to 24 fifths. So we know negative times negative is positive. So you get x plus 6 times 4 is 24. So fifths equals 24 fifths. So we know x has to be 0, right? If I subtract 24 fifths away from each side of the equation, we would get x is equal to 0. So y equals negative 4, x equals 0. So you can pause the video, check and make sure that's the correct solution. The ordered pair 0, negative 4. Now, I want to talk about reduced row echelon form. So we're going to go back to the row echelon diagram I gave you. All right, so we know at this point that row echelon form is 1s down the diagonal, a 0 below, and you have real numbers A, B, and C. So with this form, we have the information to go back and plug into the system and get our solution. But with reduced row echelon form, we don't have to go back and plug things in. We have our solution. So let me show you that. This is called reduced row echelon form. So I would have 1s down the diagonal still. So this is a 1 and this is a 1. But everything in terms of the coefficients other than down the diagonal is going to be a 0. So it's a 0 here and a 0 here. And then you have two real numbers here on the right side of your vertical bar. So let's just say this is A and this is B. So with this guy right here, I don't need to use substitution because I know that 1x, or just x, is equal to A. So x equals A, and then 1y, or just y, is equal to B. So I have my solution in this form without going back to plug things in. So you might ask the question, which one is faster? Well, generally, reduced row echelon form is going to be a little bit quicker because we don't have to go back and plug things in, right? We have x equals something, y equals something. So I want to just show you on that last example. So this is where we kind of stopped and used substitution. So let's pretend that we continued. So let me just copy this and bring it to a fresh sheet. So we already know y equals negative 4x equals 0. In order to get that information, I want to make this part right here, into a 0. I already know that y is negative 4. I've got that information. But I want to know x is equal to what? So how could I make this into a 0? Well, you've got to think about what I could add to negative 6/5 to get to 0. Negative 6/5 plus what? This is easy. 6/5 equals 0. Well, since this is a 1, I just need to multiply this by 6/5. So if I multiply row 2 by 6/5 and add it to row 1, I'm going to get what I need. So let's set this up here. So let's set up row 2 is 0, 1, and negative 4. So that's already there. 0 times 6/5 is 0. 0 plus 1 is 1. 1 times 6/5 is 6/5. 6/5 plus negative 6/5 is 0. Negative 4 times 6/5. So negative 4 times 6/5. Negative 4 times 6 is going to give me negative 24. So I'd have negative 24/5. Now, negative 24/5 plus 24/5 is 0. So what did I find here now? I found that x is equal to 0, which is what it is. Y is equal to negative 4, which is what it is. So with this form, I don't need to go back and plug things in. Okay, so in most cases, it's just a little bit quicker. All right, but I want you to understand both forms because you might get tested on it. So you have row echelon form, which is this, and you have reduced row echelon form, which is this.